In this module, we are going to look at some useful tricks for integrating functions of one variable. There is nothing special about these tricks. This is just sort of a compendium of ideas that are useful. In the end, it's all about you practicing a lot of problems and developing intuition for how it's done. But hopefully this will still be useful. So the first one that we are going to look over is called algebraic substitution. And so let's see how this works. So let's say you have to integrate for whatever reason this particular function 1 over x squared a to the power minus x dx. It looks horrible. I have no idea how to do it at first glance. But then you do know that if it was just a to the power minus x, you do know how to do it. Actually, let's make it even more complicated. Let's make it e to the power minus 1 over x. Let's say this is what we have to integrate. So if it was e to the power x dx or e to the power minus x dx, then we knew how to do it because we remember the derivative of e to the power x. So what can we do here? We can make a substitution of variables. Let's introduce a variable y defined as y is equal to 1 over x. If we do that, this integral becomes 1 over x squared, but x squared, 1 over x squared is now y squared, and e to the power minus 1 by x would become e to the power y. We still have a dx. We have to think about dx. So what do we do with dx? We know that dx is equal to d of 1 over y in this case. So that is the same as minus d over y by y squared, right? So this will be minus dy by y squared. So now the y square and y square cancel, and it becomes integral minus e to the power y dy, which is minus e to the power y plus some constant c. And now we can substitute back the value of y, which is minus e to the power 1 over x plus some constant c. So we have been able to change this horrible looking integral into something we could do easily. Now, this might have been a 1 over x cube over here. Then this trick would not work as simply, and we will see how to deal with that. But many times, simple algebraic substitutions solve our life. So if you find something complicated that you don't know, try to see how can you change it into something that you do know. In this case, it was e to the power minus something complicated, and we changed it into e to the power something that we do know. Second substitution or transformation that is very useful is a trigonometric transformation. So trigonometric transformation. I'm just going to write it trans. So for example, if we're interested in sine square x dx. So this is again going to be difficult to do, but if you do know a corresponding trigonometric identity, then you should use it. In this case, the relevant identity is sine square x is equal to half of 1 minus cos 2x. If you use this identity, then this integral becomes half 1 minus cos 2x dx, and we saw integral of a constant and we saw integral of cos ax. So this thing is simply half over x minus 1 by 4 sine 2x plus c. So by using a suitable trigonometric identity, we were able to make this integral easy. Third one, which shows up a lot, is called partial fractions. Where you have integrals of the form dx of x minus a by x minus b. Here, it's hard to do on its own, but what we can do is to make use of a very clever identity which says that 1 by x minus a by x minus b is the same as 1 by b minus a divided by 1 by a minus x minus 1 by b minus x. So you can back calculate it and see these two things are exactly the same. But now what it does for us is to change this integral into something that looks like 1 by b minus a integral dx by a minus x minus 1 by b minus a, because that's a constant, so b minus a comes out, dx by b minus x. And this is easy to perform because we know that this is going to be log of a minus x. So this simply becomes 1 by b minus a log of b minus x by a minus x plus c. Here I skipped 2 steps in the exercise. I will have you go through them and look at it carefully. If it's not obvious to you, then something is missing. You should go back and think about it. Why is it not obvious to you? And this over here, pardon my handwriting, is a constant c. The fourth example that we are going to look for is actually super, super important. So I'm going to make 3 stars over here. Well, let's make a 4 star because it's so important. It's also one of my favorite relations. It's called integration by parts. This allows you, and actually all the 3 examples that we did so far could have been redone using integration by parts, and that will also be a part of the exercise when you will look at it. Integration by parts uses the product rule that we saw for derivatives, which you will recall is something such as d by dx, u of x multiplied by v of x is equal to u of x dvx by dx plus v of x du of x by dx, right? So this was our integration by parts. What does this mean? Let's multiply both sides by dx. So we will get d of uv, and instead of writing u of x and v of x, I'm just writing u and v. So this means v of x. This means u of x. This is going to be u dv plus v du. That's all I have done. This itself can be written as u dv is equal to d of uv minus v du, which leads to the relation integral of u dv is equal to integral of duv minus integral of v du. But what is integral of duv? That is simply uv, right? Like all the first property of an integral. If we differentiate uv, then we will get duv minus integral v du. This is a very useful result. And this is the integration by parts formula. For example, let's consider the integral 0 to infinity x e to the power minus ax, and you could do it for definite and indefinite integral also. Here we are doing for definite. And let's try to calculate this integral by using the integral or derivative integration by parts formula. So let's write it in the form u dv. So what do we have here? We have u is equal to x, or du is equal to dx, and so all of this is now dv. So dv is equal to e to the power minus ax dx. What does it mean for v? Therefore v is minus 1 by a e to the power minus ax. So if we use both of these and put it in this formula, we get, and we put it in this final formula, then we get integral 0 to infinity x e to the power minus ax dx is equal to uv minus integral v du. What is uv? uv is simply a product of both these things, but here we have a limit of the function, right? So we have to keep using 0 to infinity, and this is where you have to be careful. This is going to be uv, the difference of uv calculated at both points. So what is uv? uv is going to be x multiplied by this thing. So we have minus x over a multiplied by e to the power minus ax calculated at 0 and at infinity. So you calculate it at infinity, you calculate it at 0, and you take the difference. So we should write that here also, 0 and infinity. If it was an indefinite integral, then we won't have these limits. Minus 0, so infinity, minus 1 over a e to the power minus ax dx. And now we can do this, and it boils down to ignoring the second term, which you can see due to L'Hopital rule, that this second term, the whole thing goes to 0. This is an exercise for you to check why this happens. This goes to 0. All we are left with is the first term, and the first term is equal to 1 over a squared. So we have been able to calculate our integral using the integration by parts rule. So it seems a bit alien at first, but it's the more you practice this rule, the more comfortable you will become with it. Let's look at another example of integration by parts. Let's say we have to calculate integral x sine x dx. So we know what is the integral of x, we know what is the integral of sine of x, but we don't know what's the integral of x sine of x. So let's say this is now our u dv. So we can see what we have here. We have u is equal to x, therefore du is equal to dx. And this first term doesn't have to be just x, it could have been x squared. And we have dv is equal to sine x dx. So what does that mean? That means v must be minus cosine of x, right? So now we can use these rules. And in this case, we are doing an indefinite integral, so no limits. So integral x sine x dx will now be uv minus integral v du. So you see, what's the whole point here? We are using it in such a way that du becomes a simple variable dx, and we have a function v here, which we know what does it integrate to. So this will be u multiplied by v, which is minus x cosine x, minus cosine of x dx. So this is minus x cosine x plus integral cosine x dx. And we know that is going to be sine of x. So this is minus x cos x plus sine of x plus a constant. And this was quite a nice application of integration by parts. Otherwise, it will be very hard to do. And you can also try to do things such as integral x e to the power dx. In fact, you could try to think about integrals such as x to the power n ex dx, and all of these become very useful and very easy to calculate if you know how to do integration by parts. And in the associated exercise, there are many more practice problems for this along with answers. That brings us to the end of this module. In the next module, if you will take all the stuff we have done with differentiation and integration so far in one variable and try to think about what happens in multiple variables. And that's also going to be a lot of fun. Thank you very much.